Greetings. So these are the people who created quantum mechanics, or the major contributors, and Niels Bohr is at the center, who overcame all the arguments against quantum theory. And the way we usually learn quantum mechanics in our courses, we learn about the wave particle duality, which is the de Broglie-Schrödinger approach to quantum mechanics. We learn about the matrix mechanics, the uncertainty principle, and the Heisenberg-Born-Jordan approach to quantum mechanics. And the focus of today's lecture is the third approach to quantum mechanics, which is the Feynman path integral approach. And in this approach, we consider the probability amplitude that a particle at an initial state x0 at time t0 propagates to x prime t prime is given by this integral. All right, so this is an integration over several variables, because you segment the x prime minus x0 interval into infinitely different hops. You can hop from point here to here and then to here, or you can hop from here to here and then to here, or any which way. All right, and there are these infinite paths which are available to the particle, and this is integration over all of those segments. And S is the action, which is the definite integral, which represents the action integral L dt, which is again a functional, because it is over several integration variables. Now this is a completely new idea. It's different from the de Broglie-Schrödinger idea, in which you say that, okay, a particle is represented by the wave which satisfies the Schrödinger equation, all right, or dynamical variables which are represented by operators which evolve with time according to the Heisenberg equation of motion. So that's another way of, so those are the familiar ways which I call as conventional quantum mechanics. And here is a different approach altogether. And the conventional quantum mechanics tells us that this probability amplitude is obtainable from the time evolution operator, which we know goes as this exponential operator consisting of the Hamiltonian. Okay, so this is the usual prescription in quantum mechanics. Now, we are going to show that the path integral quantum mechanics, which is completely new in this course, means it was developed by Feynman in late 1940s. So it's not new in that sense, but new to us, or new to me at least, if not to the rest. So this approach and the conventional quantum mechanics, they give essentially the same result, and we will show this for the case of a free particle. And this common result is what is given in the last equation over here, which some of you may be familiar with from wave mechanics, but we will obtain it nonetheless. Now, it is not a restriction that we are going to show this just for free particles, because the Feynman particles do travel as free particles in between quantum scatterers. Okay? So the path between two scatterers is essentially straight, and they are traveling like free particles. So I believe that the choice that, okay, you demonstrate the equivalence for free particles is therefore not restrictive, because in between the scatterers they do propagate essentially as free particles. So that sort of generalizes it, rather than worry us as if we are demonstrating it only for a special case. So let's first remind ourselves of how this probability amplitude is obtained in conventional quantum mechanics. So, you have to determine this matrix element, right, which for a free particle the Hamiltonian consists of only the kinetic energy operator. There is no potential energy part because the particle is free, there is no interaction. So, you write the Hamiltonian for the free particle, and now you cannot the x0, the position eigenstates are not eigenstates of the Hamiltonian. Hamiltonian consists of the momentum operator, the square of the momentum. Now, that is not a problem because you can insert a unit operator, resolve it in momentum eigenstates, okay, and now allow the kinetic energy operator to operate on momentum eigenstates and pick up the eigenvalue, okay, and once you pick up that eigenvalue, you can write it as this, right, okay. So, it is a completely legal operation. So, having done it, you now write the wave functions in the conventional function form rather than the Dirac notation. So, you have two complex conjugate over there. So, it is e to the I px and e to the minus I px, all right. Right. So, you have got x prime on one side and x on the other, and the two together give you essentially, along with the term that you got from the eigenvalue of the kinetic energy operator, which is p square by 2m, along with that you get essentially a Gaussian integral. And we discussed how to obtain this Gaussian integral, which is a very straightforward thing, but in our previous class we have actually discussed it. So, remind yourself of that, and using this Gaussian integral you get the result that this propagator, this probability amplitude is essentially some number multiplied by a phase factor by cosine and sine terms, okay. So, it can be broken up into an amplitude part, and no matter what the path is, okay, this amplitude is going to be the same, but the phase will change. Now, this is what we get from conventional quantum mechanics. So, let us see how this result agrees or does not with the path integral approach. So, this is the conventional quantum mechanics result. So, I have marked it with a star so that we remember this, and having gotten this, we will now ask what does the Feynman path integral approach, which is this integral which is in terms of the action, okay. This is the same classical action integral L dt. So, the same idea is used over here, and what does the path integral approach give us is our question, all right. So, this path integral approach basically as I said, it is a set of multiple integrals because there are infinite paths available, and the integration over time is again it is the limit of a sum over which the time interval is chopped into tiny time intervals delta t, which are infinitesimal in size, but there are infinite of them, okay. So, that is how you perform these integrals. So, this is the integral in which you have to determine the action, which is an integral of the Lagrangian. So, the Lagrangian is t minus v, which is nothing but t for a free particle, and that is all we really care for. So, we write the path integral probability amplitude in this form, and notice that we can solve this integral by introducing a dimensionless variable. It makes the writing a little easy so that you do not have to write too many things, otherwise you have to write the m and the h cross every time. So, to avoid that, instead of the variable x, you introduce a variable y, so that the integration over x will be integration over y, or okay, and you can write this as integration over y instead of integration over x, all right. So, it takes some time to write this out carefully, correct the careless mistakes, but then at a glance you can see that it is a very simple thing which an undergraduate student can do easily, right. So, all you have done is to transfer the integration variable from x to y. Having done that, we now simplify this integral. So, first thing to note is to see that what you see in this circle, there are many things which cancel out. You have got an h cross in the denominator here and h cross in the numerator here. You have got an m over here which cancels this m, this 2 cancels this 2, and then there is all right. So, all of these things are taken care of. Okay, and then you write an equivalent form after cancelling all that. And let us take, just to illustrate how this integration is done, we said that there are infinite steps that you can take, but let us take only one hop. So, the particle goes from here to here and from here to there. Okay. So, there is only one integration involved, which will be in this case over the variable x1, which we are now going to do over the equivalent variable y1, which replaces x1. So, you are interested in evaluating this integral over y1. Now, if you see, the exponent here has got this square of this difference. So, let us factor out this constant outside the integration, there is no y variable over here, and the rest of it is this difference which is y2 minus y1 whole square, but you need to sum over 1 and 2. So, this is y2 minus y1 square plus y1 minus y0 square. Okay? So, there are two terms over here. So, there are these two terms which come here. Let us expand them. So, y2 minus y1 square is y2 square minus 2 y1 y2 plus y1 square, and similarly you expand this term, right, and you get these three, and then you can combine these summations, common terms in both, because you have got a y1 square here and a y1 square here. So, that will give you a 2 y1 square here, and you combine these terms and this is what you get. And now you see that it is in the familiar Gaussian form. Okay? And these Gaussian integrals which we discussed in the previous class have this result, that you first evaluate the integral I, which is e to the minus ax square, and then if you add bx to that, then you get a different result, but which is easily obtainable from the previous result. So, these are the only two integrals that we really need, and the integral that we are looking at has exactly that form. You have got an ay square and plus by. Okay? So, there is a y1, the integration variable is y1. All right, you can call it, it's a dummy variable which gets integrated out, you call it y1 or just y or x or whatever you call it, doesn't matter, and you use the Gaussian integrals to evaluate them. And this is the result, that if the integration over x of e to the minus ax square plus bx is given by this. So, you need, the result will be root of b square, root of pi over a, and then you will have e to the b square over 4a. So, this is the common factor which we should not forget. This is one of the things that you miss when you make careless mistakes, right. And then the rest of it, you need the b square, which is here. What is b? B is this coefficient of y1. So, it is the square of this minus 2i y0 plus y2, which is here. So, this is b square over 4 times a is minus 2i, okay, and rest of it is just rearrangement. So, you put everything together and you have this final result. Right? You can see that? Good. So this is the y1 integral. Now this is what would happen if you were to take only one step, but you are going to take infinite of them, right? So let us see what happens if you take the y2 integral. Okay? When you take the y2, you get, if you move on this way, y2, y3 and so on, you get nested Gaussians, a Gaussian within the Gaussian and so on. Okay? You have already seen in the first step how that happened. So you will get nested Gaussians, and I will let you work it out. Sit down with a paper and pencil and actually evaluate these integrals. They're very simple. I've shown you how they work. Okay? And then you can simplify this. So here you have got an integration over y1, y2 all the way up to yn minus 1. Then you have got the square root of this to the power n, and then you have this exponential, but now you are summing over all the way from j going from 1 to n. In the first example we just had n equal to 2, so j went from j equal to 1 and then j equal to 2. So there were only 2 squares of the differences to be added. Now you have so many of them, and then you have to combine the terms. Okay? So it is a little bit lengthy, but not at all difficult. And then the result is you have to take the limit n going to infinity, but then the delta t will also slowly shrink to 0. It will become infinitesimally small. But the n times delta t will be finite. It will be the time difference from ti to tf, from the initial time to the final time. So this is what we have. Let us rewrite it in terms of the original variable x, because that is what we are interested in. So we just avoided writing these extra symbols in between, but now we need them back. So we rewrite this in terms of the original variable, which is x, and now n into delta t, n goes to infinity, delta t becomes infinitesimally small, the product is finite, okay? And that finite is the time interval from the initial time to the later time. So you put n delta t as t prime minus t0, and the result is amazing. It is just what you got from conventional wave mechanics. It's exactly the same. So you began with a completely different ansatz, which has nothing to do with a wave, which has nothing to do with a wave function, which has nothing to do with the Schrodinger equation, except that it turns out to be completely equivalent to that. Okay, the ansatz is in terms of the propagator which Feynman introduced, which gives you the probability amplitude of a certain process, which in this case is a particle going from x0 t0 to x prime t prime. Okay? And this probability amplitude, whether you obtain it using the Feynman ansatz or the de Broglie Schrodinger ansatz, okay, either which way you get exactly the same result. And this is very satisfying because in between the quantum scatterers, the Feynman particles travel essentially as free particles. We have shown it only for a free particle, but you don't need to do anything more than that, because in between the scatterers, the Feynman particles propagate only on that, and then of course there is the interaction and so on. So this is the conventional wave mechanics and matrix mechanics that we are familiar with, wave mechanics of de Broglie-Schrödinger and the matrix mechanics of Heisenberg, Born and Jordan. Okay? This is the conventional wave mechanics and matrix mechanics that we are familiar with. The Feynman mechanics is equivalent to that, right? It corresponds to that, and now we get the full picture that Newton's law works because they are compatible with the Lagrange-Hamilton formalism, which makes no use of the idea of force. It's based on the principle of variation, the Hamilton's principle of variation, right? And the Newton's law makes no use of this variational principle. The variational principle makes no use of force, but Newton's law corresponds to the Lagrange-Hamilton principle, and the Lagrange-Hamilton principle makes use of a variational principle which we will show is an approximation to quantum mechanics, and it's a good approximation, and that is the reason Newton's law works. Okay? Although the idea of force is something that physics dispenses with when you get to relativistic phenomena and quantum phenomena, and not because you are using a different theory, but because nature demands a different theory. So the laws of nature are relativistic and they are quantum mechanical, so the idea of a force really cannot really survive. It is not sustainable. So let us consider, we now need to show that, okay, why the classical mechanical solution, the Lagrange-Hamilton solution, is an approximation to quantum mechanical solution. So we will show that it is a good approximation to the Feynman path integral approach. So let us consider the same problem. x0 at time t0 is where is what describes the initial state of the particle. The final state is x prime t prime, right? And there will be infinite ways of getting there using the Feynman path integral approach, right, which is given by this Feynman sum, right, which is sum over all the histories, sum over all the infinite paths that the particle can possibly take, right. So this is what gives us the description of this probability amplitude in Feynman approach. So there are infinite paths which are possible, and we are going to ask why in classical mechanics a particular path results. What is that path? What is that path in classical mechanics? It's a free particle, there is no force acting on it. So it starts from x0 t0, gets to x prime t prime, right, with no intermediate interaction, okay, and somewhat like the Galileo-Newton law of inertia, the particle would propagate at a constant momentum and it will get there in a straight line, right. So that is the classical path that you expect. All the alternative paths which Feynman requires you to consider, they will end up cancelling each other because of the phase term, and that is what we are going to show now. Okay? So you have a free particle and the classical path is this straight line path, PS. Okay? You can also think of some alternative path. Feynman admits that there are infinite paths and anything that is possible will happen. So you have to include that possibility. So we will consider an alternate path which is a quadratic path, which we know from our intuition and also from what we have learnt in classical mechanics, and quantum mechanics is not going to conflict with that. But the path integral approach requires you to consider infinite alternative paths. So we will consider one of these alternatives, which is this quadratic path PQ. Okay? And then ask the question, why is PS right and PQ wrong? why is it that nature picks the path PS and not PQ? That is the question we have to answer. Okay? So, let us see how it works out. So, let us first consider the straight line path, and this path is given by x changes with time, x changes linearly with time, okay, at a slope which is dx by dt. So, we have x as a function of time, we get x dot which is the time derivative of x, which is the velocity, okay. And now we have got the velocity, we construct the kinetic energy from which we will consider the Lagrangian, which is what we need for the path integral, right. So, we consider the Lagrangian, which is half mv square, there is no potential term, it is a free particle, okay. This is the Lagrangian, and now you have the Lagrangian, you can determine what is the action, which is the integral of the Lagrangian, integral L dt, okay. So, you determine the action, got it, and now you put this in this Feynman propagator. So, put this in and you will get the probability amplitude for the transit, but ask yourself what is the phase? Phase is action divided by Planck's constant. So, to what extent is action larger than h cross? Action in units of h cross. H cross is the quantum of action, h over 2 pi. H is the quantum of action as we normally define it. So, the phase which is a measure of how strong the action is compared to the quantum of action. That ratio, that phase angle, as you can see, is action divided by h cross, which is mx square divided by 2 h cross t. The subscript f is coming for the final time, okay. We have assumed that the original time is 0, otherwise there would be a t2 minus t1 type of thing, but t1 the initial time we take to be 0, so that we do not write too many things, okay, but it is the same time interval. So, this is the phase that you get for the straight line path. What is the phase for the quadratic path? Let us do the same for the quadratic path. So, the quadratic path, the x goes as the square of t. So, x dot goes linearly with t, that is the velocity. The velocity square will go quadratically with t, that is the square of the velocity, which will go into the kinetic energy, which will go into the Lagrangian, right. And then you have to determine the action for this Lagrangian, which goes quadratically with time, and in this case you can see that the action, can you see this? So, you have it is worked out over here, the action turns out to be to go as x square over tf, okay. In the previous case also it was the same, but the factor was not 2/3, it was 1/2, okay. Now it is 2/3. So, now you can put this in the propagator, in the Feynman propagator, and get the probability amplitude. Look at the phase, it is now 2/3 mx square over h cross t, and you can see that in the quadratic case the phase angle is larger than this, which is interesting, but there is a more deeper question that we need to address. So far so good. We have determined the phase for the two paths, for the straight path and for the quadratic path. For the quadratic path, we have seen that the phase angle is greater than what you get for the straight path. But that this phase angle is greater than the straight path, the corresponding angle for the straight path, is not just the reason. There is a deeper reason. The deeper reason is that if you change these paths, because Feynman path integral approach requires you to consider all the infinite paths. So, if you vary the straight path, you have a straight path and you vary it slightly, or you have got a quadratic path and you vary it slightly, what will the neighboring paths contribute? Okay, so that is the question we have to ask. And let us actually do that. Let us actually vary these paths, carry out a perturbation of these paths, change these paths slightly and see what they contribute to the probability amplitude. So, we will now change these paths by adding a tiny perturbation. So, this is the original path. The straight line path is a linear function of time, the quadratic is a quadratic function of time, and to the time variable we add a perturbation which is 1 plus epsilon times t minus Tf by Tf. Okay, so t minus Tf by Tf is a ratio. So, you have got a dimensionless small number which you add to unity. If epsilon is 0, you get the original straight and quadratic paths. When epsilon is a tiny number, you add a small perturbation, not very big, a small perturbation. So, that if you develop your solution in a power series in epsilon, you can decide on a truncation level and say to what order you can neglect terms. Okay? So, we will develop an approximation scheme in orders of the perturbation parameter epsilon. So, this is a variation in the straight path, and in the quadratic path you vary t by exactly the same perturbation. Mind you, watch this figure, watch this slide very carefully because there is no cheating involved. In both cases the perturbation is exactly by the same factor, which is 1 plus epsilon times t minus Tf by Tf. That is the perturbing factor. So, it is not that you are considering different perturbations to the straight path and different to the for the quadratic path. So, you take the straight path and vary it. So, S for straight, V for variation, the subscript S for S and V stand for variation of the straight path. Okay? So, we evaluated this for the straight path, now we evaluate it for the varied, the change straight path. And now you do exactly the same thing, determine what is the, you have just rewritten it, you have multiplied t on the right, okay. Then get the velocity, then get its square, get the Lagrangian, determine the action and determine the phase, which is S over h cross. Okay. So, the steps are very simple and we have them in our mind. So, you get the velocity, now you get the square of the velocity because that is what you need in the kinetic energy term, which is what will go into the Lagrangian. So, in the square of the velocity, what kind of terms do you get? You get a term which is 1, of course, then you get a term which is linear in epsilon and a term which goes as the square of epsilon. Okay. So, now you can see that there are different terms contribute to different extent because epsilon is your perturbation parameter. So, the term in epsilon is more important than the term in epsilon square. So, remember that. So, this is what you get for the velocity. Now, you need the velocity square and put that in the Lagrangian and determine action. Okay. And if you now evaluate this action, it turns out to be different from what you had for the straight path, but the difference is of the order of epsilon square. There are terms of the order epsilon in this and they cancel each other exactly. One comes with a plus sign, the other comes with a minus sign. So the linear terms cancel. What you are left with is only the quadratic term in epsilon. Okay? So for the straight path, if you vary it slightly, if you ignore epsilon square and higher terms, then you get the same action as the original action for the exact straight path, which means that neighboring paths contribute equally as the straight path, and they will all superpose constructively because they are contributing the same thing. Okay? Now let us do this for the quadratic path. So now the quadratic path, which went as t square, now it goes as t multiplied by this perturbation term and the square of that. So now this is the x as a function of t, qv stands for the variation of the quadratic path, q for quadratic, v for variation. So x qv goes as this. Now you have got the velocity. So you simplify these terms, and this is straightforward algebra. All you are doing is you take the square, combine certain terms, factor them comfortably, right, as per your convenience, and you get velocity. You will get terms which go as epsilon to the power 0, which do not depend on the perturbation at all, which go as the first power of epsilon, and which go as the second power of epsilon. This is in velocity, but you are going to need the square of the velocity in the Lagrangian. So you will get epsilon to the 3 and also epsilon to the 4, right, when you take the square of this. So you will have terms, v square will have terms of order epsilon to the power n, with n going from 0, 1, 2, 3 and 4. So those are the terms that you will get in v square. And if you ignore epsilon to the cube and smaller terms, because we need to see only what happens up to epsilon square. We are not throwing epsilon square, we are throwing epsilon cube. But in both we are keeping terms up to epsilon square when we vary the straight path and also when we vary the quadratic path. We keep terms up to epsilon square. Okay? So epsilon cube, if you ignore, then this is what you get for the v square, and now you have to integrate over time. So you have to integrate terms like t cube, t to the 4, so you will get t to the 5 divided by 5 and so on. So you will get various terms. You put them all together and simplify the terms, and what you get from the simplification, it takes one or two simple steps, high school level steps to do this simplification. What do you get? You get a term which is independent of the perturbation parameter. So that will give you the same action as you got for the quadratic, for the strict quadratic path. And then from the variation, you get a term which goes as half of the perturbation parameter plus terms of the order which go as square. So here is the consolidation of your results. What happens when you vary these paths? We consider two paths, one a straight path and the other a quadratic path. The straight path gives you terms which are the same as the straight path if when you vary, except that the correction is of the order of epsilon square, whereas the quadratic path gives you the same as the quadratic path, but the corrections are much larger. They are of the order of epsilon rather than epsilon square. Okay? Which means that the nearby paths reinforce for the straight path. whereas for the quadratic path, the nearby paths cancel because this is a phase, so it goes as e to the I theta, which is cosine theta plus I sine theta. These are oscillatory, they go up and down between -1 and +1. So, a contribution from one will be cancelled by contribution from the other, okay, because of this. So, the nearby paths. So, now we know why nature picked the straight path, which is the classical path, okay. So, paths which are near a classical trajectory, they add up in phase, and paths which are away from the classical trajectory, they cancel each other. And if you represent these phases on a phase diagram, which is a complex, in a complex plane, you have the real part of the phase and the imaginary part, right, the cos theta and the sin theta. Then you can represent it by a vector, okay, the plane polar coordinates if you use, then this equivalence is immediate. The complex numbers can be represented by vectors, right, and some vectors add up in phase, giving you the classical path, and the non-classical paths, they end up destroying each other because all those vectors are oriented differently. Okay, the complex numbers have got phases, angles which are different from each other, and they end up cancelling each other. And this now tells us why the classical path is so commonly seen in nature, because whenever the classical action is much larger than the quantum of action, which is h, that ratio is coming into the picture all along, right. So, when the classical action is much larger than the quantum of action, then the neighboring paths add up in phase, and that is the reason the Lagrange-Hamilton equation works in classical phenomena, or phenomena which we can describe by classical mechanics, and for other we need quantum mechanics. So, let me stop here, and I will continue from this point in the next class.